Hello everyone, my name is Saeed Taheri, and today I will present GoAT, Automated Concurrency Analysis and Debugging Tool for Go. Before jumping into the design of GoAT tool, first I briefly introduce Golang and the motivation behind our work. Go is an open source language developed and maintained by Google since 2009. Go's concurrent semantics are based on horse communicating sequential processes or CSP calculi. Many projects are written in Go, such as some cloud services in Netflix and Uber, and containers like Docker and Kubernetes. Concurrency in Go is centered around Go routines and channels. Go routines are functions that execute concurrently. We can look at them as application level threads that have their own stack and are handled by Go runtime. Channels are typed conduit through which Go routines communicating. By default, sends and receives block until the other side is ready. This allows Go routines to synchronize without explicit synchronization. Other concurrency primitives such as mutexes are also available in the language to facilitate concurrent programming. Go runtime handles the interaction between concurrent components, and the runtime enqueues runnable Go routines into a global queue. The runtime also executes Go routines on CPU processors by acquiring an OS thread and stealing jobs from the global queue. Successful languages are deployed faster than debugging support can keep up. This is a snapshot that I got from the official Golang 2019 survey collected from Go developers describing the importance versus satisfaction of different factors of the language. It shows that the available concurrency debugging mechanisms have the lowest satisfaction, while the importance is around the median. And this was one of the main motivation of GoAT work to address this lack. Concurrent bugs in Go are categorized into blocking and non-blocking bugs. Blocking bugs are when the program execution does not reach its final state, such as deadlocks, and non-blocking bugs are when the program successfully terminates but with incorrect results, such as data race. Since Go combines concepts from both shared memory and distributed memory systems, the blocking bugs in Go are caused either by circular wait on resources or by wait on send or receive from a channel, or a mixture of both. Also, partial deadlocks are very common in Go, where application-level Go routines leak from execution because the main Go routine terminates successfully and there is no restriction on spawned Go routines to join before the program termination. In GoAT, our focus is on blocking bugs. GoAT is an end-to-end framework that combines static and dynamic approaches to facilitate automated trace collection and analysis for concurrent Go. We designed and implemented GoAT having three main objectives in mind. First, we want to gain insight into the dynamic behavior of the program through automated dynamic tracing to enable offline analysis. We have enriched the standard tracer package with concurrency primitive events to obtain accurate and rich execution concurrency traces, or ECTs. The figure on the bottom right shows the distribution of number of trials falling into 4 given intervals to detect 68 blocking bugs in the GoCare benchmark. It shows that more than 30% of bugs take more than one execution to occur. Such bugs are called Heisenberg bugs, since they are rare to occur and difficult to reproduce. As our second objective, we apply the well-known method of bounded delays to systematically explore the interleaving space and accelerate the exposure of such bugs. Delaying concurrent components to expose bug has been well studied before. However, in the context of modern languages such as Go, it has not been tested and implemented. So what is novel in GoAT is the implementation of the idea in the context of Go. We statically obtain the concurrency usage model M, which is a table of concurrency usage source locations. Then we inject bounded yields before them because the behavior of concurrency primitives define the blocking behavior of the program. And perturbation around concurrency usage has been proved to be efficient and effective in exposing bugs. In offline, we analyze the ECT of execution to see if any partial or global deadlock has happened. Finally, to measure the quality of our interleaving exploration method, we derive a set of rich concurrency coverage requirements from the concurrency usage model to measure during testing iterations and make sure that we are covering possible concurrent scenarios during the testing iterations. And at last, once we detect a bug or we reach an upper bound for coverage percentage, GoAT terminates testing iterations and generates reports and visualizations for the user for further analysis. Now I briefly explain GoAT's workflow through an example. This is simplified version of a commit in Docker labeled as buggy. A container with a mutex and channel is instantiated in main. Two Goroutines are spawned to execute functions monitor and status change concurrently. Function monitor is an infinite loop that periodically checks for the values to receive from the container's channel. If the receive is available, monitor receives from the channel and returns. Otherwise, it locks and unlocks the mutex and iterates again. Concurrently, function status change locks the mutex, send a value to container's channel, and then unlocks. In a successful execution of this program, monitor Goroutine executes one iteration of the for loop, then status change sends to the channel while holding the mutex. It blocks because there is no receive waiting. Consequently, monitor gets to execute again and unblocks the blocked Goroutine. However, in another scenario, if a context switch happens right after the select in monitor, status change holds the lock and blocks on send. Then monitor also blocks on acquiring the lock since it is held by the other Goroutine. We call this scenario a leak situation or partial deadlock because at least one Goroutine did not reach its final state and leaks from execution while the main Goroutine terminates. To analyze this program, we first statically construct the concurrency usage model. By traversing the source abstract syntax tree or AST, we identify the concurrency usage in the source and inject them to models table. Now we want to instrument the source and equip it with tracing mechanism and inject yields before concurrency usage. Through another AST traversal, first we inject handlers to the beginning of the main function to enable tracing from beginning until the end, and watch for execution liveness in case of a global deadlock. Also, we inject yield handlers before each concurrency usage to invoke the function runtime.gosketch randomly within a bound D. Runtime.gosketch pushes the current Goroutine into the tail of the global queue of runnable Goroutines, allowing all other available Goroutines to execute first. And D equals 0 over here means no schedule perturbation. We propose a set of coverage requirements to reflect the possible behavior of concurrency primitives and use them to measure the quality of scheduled space exploration. To understand the concept, let me walk you through a simple example. We have two Goroutines G1 and G2 that are communicating through a channel. If G1 gets to execute first, the send blocks G1 because the receiver is not ready. Then G2 executes the receive and unblocks G1. It could be the other way around, where the receive is blocked and the send is unblocking. From this observation, we say that two possible behavior for sends and receives are either blocked or unblocking. Similarly, we define the possible behavior for each concurrency primitive. We want to make sure that during testing, each concurrency usage behave as all possible behaviors at least once. No op is for the operations that does not fall into any of the other categories. For example, send and receive on buffered channels where the buffer is not empty and not full are neither blocked nor unblocking, so they are no op. From the coverage requirements and the concurrency usage model that we extracted, We form this table and expect to cover each entry during testing iterations. So far, we have constructed static models from the concurrency usage and defined a set of coverage requirements. Now we want to capture the dynamic behavior of our models by tracing. The alphabet of a standard execution tracer of Go is a total of 49 events. We categorize them into 6 major groups, as you can see. Although the event vocabulary is rich enough to model comprehensive Go routine latency, it lacks concurrency primitive usage events for the construction of concurrency models. So we enhanced the tracer package with concurrency events to gather evidence about the concurrent aspect of the program during execution. We call the collected trace from the enhanced package execution concurrency trace, or ECT. To evaluate the overhead of our tracing mechanism, we measured the runtime of native run, standard tracer, and the ECD tracer on the concurrent prime sieve program, which dynamically creates Go routines and has extensive channel operations. For number of Go routines below 64, the overhead is less than 50%. However, for higher number of Go routines, the overhead increases exponentially because of the extensive concurrent actions of the program. Still, it shows that ECT is applicable to programs with such large number of Go routines, even though it incurs high overhead. In offline, we construct a Go routine tree from the ECT, where each node represents a Go routine. The parent-child relation is based on the location of Go routine creation site. We implemented a mechanism to measure the progress of each Go routine based on the type of the last captured event. To check if the execution is suffering from any type of deadlock, we execute the deadlock check procedure on the Go routine tree, which is basically a BFS traversal that checks the stack and type of the last event on each node. To measure the coverage, we maintain a global Go routine tree during testing iterations, and after each test execution, we analyze the ECT to see which coverage requirements are covered. Then we accumulate the covered requirements in the global Go routine tree, and at the end of testing iterations, we can check the coverage percentage of the whole program to see how much of the interleaving space we have covered. This is the coverage table of our example. 60% of requirements are covered in the first run where the bug did not occur. In the second run, the highlighted boxes are the coverage requirements that triggered the bug. Overall, after the bug is detected, we have reached a 73% coverage. Not all the coverage requirements are coverable due to the semantics of the program or the bug in the code. And the developer should be aware of the reasons behind uncoverable requirements. For example, the no-op of send in line 26 is never coverable because the channel is unbuffered. To evaluate the effectiveness of GoAT, we used the recently released GoCare benchmark, which is the simplified version of concurrent bugs in top 9 open source projects in Go. We run GoAT alongside with 3 similar tools to check the effectiveness of GoAT in detecting blocking bugs. 3 tools are the built-in deadlock detector, LockDL from CockroachDB, and GoLeak from Uber. This table partially shows the results of our experiments. Bugs are categorized based on their causes and the subcauses, which are the concurrency primitives involved in the bug. An X followed by 1000 in the parentheses means that the tool was unable to detect any bug after 1000 executions. The number in the parentheses is the minimum required number of executions to expose the bug. PDL means partial deadlock and GDL means global deadlock. The number after PDL is the number of Go routines that have leaked when main Go routine terminates. For example, the last row which is a resource deadlock, was not detectable by 3 competitor tools. It took 199 executions to get detected by GoAT with no delays and was detected by at least 1 delay after the first execution. Each tool has a strength in detecting some kind of bugs based on their causes and subcauses or their symptoms. However, GoAT could detect all 68 blocking bugs of Gopalakrishnan regardless of their cause or symptom. This figure shows the distribution of detected bugs by each tool. It shows that at least one variation of GoAT, for example, D2, which means delaying Goroutines for up to 2 times around concurrency usage, was able to detect all bugs regardless of their causes, while the second best is GoLeak with detecting around 80% of the bugs. And this figure shows the effectiveness of yields before concurrency usage. Again, GoAT with maximum of 2 yields performs the best, meaning that at least 2 yields in the program could trigger all of the blocking bugs in the benchmark within less than 100 executions. And this figure shows the gradual coverage increase over testing iterations for different values of D for one of the bug kernels. Iterations with D0 never changes the coverage percentage, meaning that the program always executed deterministically on one processor. However, for larger values of D, the coverage percentage changes over iterations, showing that yields are effective in exercising the program over the interleaving space. In this work, we presented GoAT, an end-to-end analysis and debugging framework for concurrent Go applications that provide insight into the dynamic behavior of concurrency primitives and assists with debugging. GoAT systematically explores the interleaving space of Go scheduler to accelerate bug exposure. Using GoAT, we were able to detect all 68 blocking bugs of Gopalakrishnan benchmark. We also proposed a set of coverage requirements to evaluate the dynamic behavior of interleaving space exploration. GoAT is publicly available in this URL. You can just download it, follow its constructions, and use it. As future work, we will add more features and flexibilities to the GoAT framework so that we can cover more bugs, such as non-blocking bugs, and enable comprehensive testing for concurrent applications. Thanks for listening to this talk. Please comment your questions or forward them to this email address. Thank you so much.